And we have our next speaker with us, Dr. Jeronima Castrillon. Dr. Jeronima Castrillon is a professor in the Department of Computer Science at the Technische Universität Dresden, where he's also affiliated with the Center for Advancing Electronics Dresden. He's the head of the chair for compiler construction with research focus on methodologies, languages, tools, and algorithms for programming complex computing systems. In 2014, Dr. Castrillon co-founded Silexica, that is a company that provides programming tools for embedded multi-core architectures and is now with Xilinx. The future of computing systems will be heterogeneous in nature, as was evident by the talks yesterday and today, and programming such systems is a daunting task that will become even more challenging with the advent of emerging non-von Neumann computer architectures. Dr. Castrillon believes that the so-called golden age of computer architecture thus must be accompanied by a hopefully golden age of research in compilers and programming languages. This talk discusses domain-specific languages, or DSLs as we all know them, as a promising avenue to tame heterogeneity for non-expert programmers. So the title of his talk today is Domain-Specific Languages to Tame Heterogeneous and Emerging Computing Systems. And let's welcome Dr. Castrillon. Over to you, sir.
Okay, thank you, Romana, for the nice introduction. Thank you for the invitation. So let's see if this works. I'm going to share my desktop now. Yeah, hello, everybody. So yeah, my name is Jeronima Castrillon. I'm going to be talking about some of the research that we do in Dresden on emerging architectures and also tools, compilers, languages that map down those architectures. So let me start the introduction, this talk with a very famous plot that you have to know, right? Because many of the people here are talking about this Moore's evolution and post-Moore and this era of diminishing returns. In lectures, I usually use this simplified version, right? Like up until 2005, we had the era of single cores where the cores were getting more and more complex with a lot of innovations in hardware for different kinds of things, right? Like caches, vector instructions, and whatnot. Then we started using multi-cores, and we know the reason for that, right? The NAR scaling stopped. Then we start getting the world of the power, right? So power density worlds. So we went for specialization. And somewhere now we are in the era where we're looking into things that are maybe more revolutionary, right? Like different kinds of architectures, different kind of ways we devise computing systems beyond the classical von Neumann view of a computer. And so here you have a world of a bunch of different technologies that are being researched: quantum organic electronics, molecular electronics, DNA storage, DNA computing, carbon nanotubes. There's a lot of things that are being researched. And in part, a lot of that research is also being done in Dresden. Dresden has a very strong electronics, microelectronics community right now in academia and also in industry. And so, yeah, so we get things like massive parallel and heterogeneous systems. We get things like tensor processing units, AI engines, phase change memory, where you can do computing with. You got new ways of interconnecting systems with silicon photonics. Emerging memories is a very hot topic, and in particular in-memory computing, how can we then do computations in memory? And we're going to be talking a little bit about those topics today. So you get all these chips, right? For instance, this one from Stanford, where you have a 3D integrated solution where you have different kind of technologies at different levels, specialized for something specific, right? So that's kind of the evolution of computing, and I think you guys have heard several talks in this area so far. And as you all know, so we want these computers because these computers are helping us with some societal needs, or also getting more interesting widgets, right, and gadgets. But we also need them for advancing science, for instance, in weather, climate research, computational fluid dynamics, and also then in things that go like autonomous driving, autonomous drones, and so on, where you see an ever increasing complexity of the software that we have to bring down to these very complex computing systems, right? So the result of that is that you have programmers that are overwhelmed, right? Because you, as a weather scientist, you don't want to have to understand all that complexity of hardware, right? You don't want to have to understand. I mean, you don't understand today so much the vector instructions and the cache hierarchies and communicating InfiniBand, all those kind of things. Let alone you want to understand things like an in-memory computing accelerator for doing some tensor computations, right? So that's why in the abstract that was read before, I say that this golden era in computer architectures, what you've seen of the evolution of hardware, has to come along with some new challenges or new ways we do programming of the systems, what some people call also toll-free abstractions, right? So we want to insert abstractions for programming, but they should be toll-free, which means that by using these abstractions, you don't want to lose the potential that these new computing systems have, right? So the abstraction shouldn't be, oh, let's then just keep working as if we have a von Neumann machine, and let's introduce some virtualization layers that in the end won't really exploit what is underneath in the machine, right? So that's why I care about these toll-free abstractions, so that not only those highly expert people that really understand the hardware are able to squeeze all the juice out of that new hardware, okay? So yeah, let's maybe start by why do we need new abstractions? And here you see a mathematical expression. So this is actually a tensor interpolation. That's something that is used in multiple areas of physics simulations. As you want to do tensor interpolation, if you know what that is, you just know that this is the equation that describes that. If you go and program that directly in C code, you will write something that looks like this, okay? And so here I say that this is what we naively code. If you're really a naive programmer, I think probably many of the listeners would know that this is not maybe the best way to do this. But anyway, so if you're a naive programmer, you would write something like this. And if you pass that to a compiler based on this abstraction, the abstraction here is the C language, a very von Neumann inspired kind of language. The compiler will create a model of that code that looks like this. And this is the actual compiler graph for this piece of code. And it's already simplified a bit so that otherwise it wouldn't fit the screen. And so the message here is that for a compiler, provided this graph here, is really very difficult to understand the intent of the program. It is very difficult for the compiler to understand patterns and to understand that actually what's going on here is that we have some nested tensor contractions, and there are some properties of tensor contraction that the compiler could explore if he knew that these are tensor contractions. Okay, and so in fact, if you go and write this piece of code and you give it to a modern compiler, you will get really lousy performance. And in fact, the performance that you get is more or less 100 times slower than this piece of code. So this code is implementing the same thing. This is what an expert programmer would write for a Intel CPU. Okay, this is just a single-threaded. Oh, no, it's not single-threaded because it has OpenMP4 here. So, but this code here, single-threaded, even not even consider the multiple threads. This code here would run 100 times faster than this code here. Okay, and you see that this code is more difficult to write, right? That's why I say this is what performance experts would run. And to be able to write this code, we have to know a lot of stuff from this code or from this expression that is very difficult to infer from this low-level representation. Okay, so the comment here is that today we're not, if I am given, there is something in the, oh, there was a question in the chat, but I think that's not for me. Okay, sorry. So my point here is that today, if you give this to a compiler, we are not able to really squeeze the performance of a modern Intel core in a CPU. Now, how would we expect a compiler, given this level of abstraction, to be able to identify? Okay, I can use some operations that are in my tensor processing unit, or yeah, this data is in memory, then I will just use my in-memory accelerator. Or oh yeah, by the way, this is maybe I could stream this with some high bandwidth memory in an FPGA Alveo card, right? So those are very different questions. How do we map this to a von Neumann machine? How do we map this to a coprocessor that is good in doing tensor operations? How do I upload that to the memory? Or how do I create hardware on an FPGA, right? So those questions are really fundamentally different and requires a lot of understanding of what's going on in the code that goes beyond that graph that I showed you before. And that's where DSLs kind of come in. And so in the introduction, you mentioned that DSLs are known to all of you. So that's great. So DSL is a domain-specific language. That is not to say that all the work that is being done in polyhedral compilers, trace-driven dynamic compilation, patterns, idioms, expression, I think those works are really important because we anyway have a lot of legacy von Neumann kind of written code. So we still need that research for traditional languages. So yeah, but the talk today is like, what can we do with DSLs, right? And why do I think they are cool? So this is a this is a figure that I took from a paper last year, where you see that there are some efforts trying to raise the level of abstraction of languages like C++. And so this paper was called progressive raising. Whereas DSLs will start up here, right? This is where DSLs start. That's where they kind of already give the amount, or give a lot of information about what the program wants to do, so the compiler can do lowering. And kind of the analogy here is that the higher you are, if you choose these abstractions intelligently, the higher you are, kind of the faster you go down the hill, right? And the more fun you have. And that's kind of an analogy to performance. The faster you can get things running. So yeah, so the DSLs are here to bridge that domain between, to bridge that gap between domain experts and maybe C++ and Fortran code. And there are plenty of examples of very successful DSLs out there from the world, like Halide, Spiral, TVM, TensorFlow, FireRank. So there's a lot of DSLs or frameworks that where you use Python, maybe don't even know that you're using a new language. You're using some abstractions via APIs, but at the end you're using those abstractions that could be thought of as being a language. Okay, so let me give you two examples of languages that we are working on in my group. So the first one is from the area of particle mesh simulations. So here we are collaborating with people that do computational biology with them. And the nice thing of this particle method is that you can model very different kinds of phenomena, right? You can model phenomena that are discrete or continuous, or you can model also phenomena that are deterministic or stochastic, right? So yeah, so then what we offer as a syntax you see here, like for instance, if my program is continuous, then I offer a syntax that allows me to specify what is my time loop, the time in which I want to run the simulation on. I can say what kind of temporal method I want to discretize time and how do I want to discretize space. And so there are a couple of methods that are supported, and then you just give the governing equations, right? And this is a very high level language. As you can see, there's a language that is very close to the physicist or to the mathematician that understands these equations. So that's a way to model a continuous problem. And this would be a way to model a discrete problem where you directly define some particles, you define some properties for those particles, and then in a particle-based simulation, kind of the way that the simulation evolves is by these two important methods, interact and evolve. That's where the particles interact with each other in a pairwise kind of interaction, and then every particle update its properties with the evolve methods. And so we have like abstractions for those in there. And if you have worked with particle kind of simulations, then you know that they have to be synchronized across domains, right? And there's a domain decomposition. You have to pass information to other particles in the other domain, and all that stuff, like those ghost layers and ghost synchronization, all that stuff is hidden from the programmer. That stuff is all generated by the compiler in this case. Okay, so that's kind of the syntax. I think we can agree that the syntax is high level. Today we map down to a library that's called OpenFPM. That's a very efficient C++ template library that can generate code for CPUs or GPUs. And so we generate code against this library. So to give you an idea what you would have to do if you use that library, so if this is what we want, similar to what we want before with this mathematical expression. So today in the DSL, you would code something that looks very similar to this expression. Whereas if you go into the C++ template library, you would have to write this is a 3D simulation. So you have to write this code for the different axes, X, Y, and Z. And so you see there's a lot of complex code here because the library already offers a lot of abstractions with very fancy template metaprogramming that I don't know what's the level of programmers that I have here, but template metaprogramming is hard to get right. And so if you see these expressions here, there's a lot of copy paste here actually. So it's very easy to make a mistake. It's very easy to make here you have some X, here some Y. So if you make a copy paste mistake, you forgot to change one C for one X, then you're gonna get a different kind of result in the simulation, right? So this is also kind of an issue that we want to solve with DSLs. We want to be able to reduce the surface in which you as a programmer can insert bugs. So how do we do this? Now, a bit more internally, so we like to do what we call model-to-model code generation, which means that our language is actually, as they should be there, our language is actually populating a model. So we analyze the model of particle-based simulations, what kind of things, what kind of concepts, what kind of abstractions do I need to represent a simulation? And we also model OpenFPM, right? What kind of abstraction is in that C++ implementation, so that we can then model, that we can map from this model to that model. And by doing so, we hope, I mean, in the case of this compiler, we haven't verified anything, but at least the hope is that since you're going model to model, you have less possibilities of generating bugs when you generate code. Okay. So in the end, so an expression here would look like this. So this is an expression in the DSL. So internally, we have a representation that allows us to work through the elements of that model. So this is a way to walk through the elements of the model of the DSL. And from that model of the DSL, we can then create automatically the model of we can create the code for the OpenFPM library. So actually, this expression that you see here, from this expression, you basically generate these three chunks or snippets of code. Okay. And so since here the dimensions are implicit and many things are implicit, the loops are implicit, so there is less opportunities for you to insert some errors. Okay, so I think most people would agree that an expression like this is way easier to write. So the productivity argument for DSLs is not something that you really have to defend so much. The problem is, can you get really the same performance as hand optimized code? And for that, we did some small experiments here. So you see 3 different simulations just to show different aspects of this framework. You can write a discrete model on particles, a continuous model on a mesh, or a continuous model on a hybrid kind of situation where you have particles and you have mesh, and you have to interpolate between meshes and particles and back and forth to model this thing. So on the productivity argument, you see the different amount of lines. So for instance, this was kind of the most complex simulation, and you see that it's kind of an order of magnitude less lines of code, and the lines of code are considerably less complex, right? Because these lines of code here are C++ template lines of code, so there's a little bit more complexity there. In terms of performance, at least on the left and on the right, we achieved more or less the same performance as handwritten code. Here in this case, the handwritten code, which is the handwritten code, which is the gray here, is lower, so the execution time is faster. And we actually found out after publishing this paper what was the reason for that. The people that had written this code per hand, they actually merged a couple of loops. Like loop fusion is a known compiler optimization, and that's how they achieve better performance. Of course, we can do that, but what we want to do is to find generic optimization that we can apply, not just to let's just merge those 2 loops for this use case to work. No, we still have to work on optimizations in general for this kind of simulations. Okay, second example I wanted to talk to you about is the one that actually I had shown before. That's this interpolation kernel. We work with people doing computational fluid dynamics using spectral element methods. So that's where those kind of tensor expressions come from. But you also know those tensor expressions from machine learning as well. So in that case, we were working with people working on Fortran. So we provided kind of a Fortran. This is kind of a Fortran expression that they would write in their code. And so this expression with the hashes corresponds exactly to this one here. And there's also like a C++ implementation of a DSL for, say, more modern languages. And indeed, from this expression that you see here, we were able to automatically generate the code that you saw before. So this code that you saw before, I said that this is what an expert would write. In reality, this is what the compiler wrote automatically. And this was a very good performant code, but we knew already what we had to do. So we had talked to performance experts, and so we knew more or less what kind of transformations, what kind of things make sense for these kinds of expressions. So we are encoding also the knowledge of people that have been optimizing for these machines in the compiler. So this is just one version of that code. From the DSL, it's very easy to generate multiple versions, and these are actual compiler graphs for the same expression that we saw before. And you cannot see a lot of details, but I hope that you can see that the shapes of these graphs are fundamentally different. And it is very easy for us as a DSL compiler to explore the space of possible implementations and to auto-tune, if you wish, right, to realize what kind of version works better. So it's very easy to generate all of them. Now, what we are asking a traditional compiler is that we are giving the traditional compiler one graph that looks like this, because you can think of all these variants as possible variants that a programmer can come up with, right? So every programmer could write this one or could write this one. And if this is the best one, then we're expecting a compiler, given this graph, to massage the graph, to transform, to do analysis and optimizations in a sequence of steps, so as to bring this graph to look like this graph. And if some of you have some background in compilers, you would know how difficult it is to make those fundamental changes to the control flow and the data flow of a C program. Okay. So what else have we done with this language? So we are going beyond phenomena. So far I'm just talking about phenomenon architectures. So we have actually implemented a compiler using the MLIR compiler infrastructure. And I think this is a framework that for these domain-specific abstractions, this is an excellent vehicle for research and for implementation. That's what we are using in our group. This is a compiler framework with which you can create your own intermediate languages at different levels, and then work on how you lower those levels, if you wish, all the way to LLVM and to something that executes on an Intel CPU. But you can also leave earlier and then connect to accelerators, connect to different kind of things, or connect to high-level synthesis tools for FPGAs. And that's what we're doing now, right? So we saw the results for the CPU before. We are generating code for HBM, high bandwidth memory kind of systems, and optimizing when we bring data, how you compute the data, working on coarse-grained pipelines. And this is all what we do from the MLIR infrastructure. To give you an idea of what is this MLIR, so in this MLIR, we can now encode those things that you saw as syntax, right? Like the contraction. So you see, this is a contraction, is an operator that is doing a contraction, or this is a product. This is a tensor product between these two tensors, and so on and so forth. So this is a way to, and so here this style is the way we called our language. It's a tensor intermediate language. And so in the world of MLIR, this is called a dialect. And now we can encode how this contraction could be transformed into something that looks like I first diagonalize something and then I do a reduction. Or this operation here, which is a bunch of products with a reduction, could be changed into a product with a diagonalization, a reduction, and a product and a product. And each one of these kind of algebraic identities give us new versions to how to implement that code. Okay, and these are actual transformations that we have implemented within MLIR. And what you see here is that here you have elements of our language, and here you have another dialect, which is a dialect that is already in MLIR. It's a very popular dialect for linear algebra operations that are used also for machine learning and so on. And for instance, you have there matrix multiplication, right? A matrix multiplication abstraction for inside that multi-level language stack. Okay, so what can we achieve? So this is something that we're doing in the context of a European project Everest, where we're trying to kind of provide tools, provide software development environments for a convergence between HPC, big data, and machine learning. And here we're working with people that are doing this weather simulations and also the decision making, for instance, to configure wind farms depending on what the weather simulation is telling us, right? What the wind is coming, and so on and so forth. So here are just some results that we did last year. So this is I have some newer results, but they haven't been published. So these are some old results from last year, where we see at least things that we can do from our DSL. For instance, we can tell a memory generator how to generate the memories in the FPGA system, so that we can reuse the memory blocks in the FPGA, and therefore we can reduce the amount of resources that we need in the FPGA. So instead of, if we don't have any sharing, so if the compiler doesn't provide any information to the memory generator about the sharing, we would need here twice as much memories as in this optimized version by the compiler. And this is just to speed up. So you see, and then the difference here is how many modules are we exporting. So this would be in software. This would be, if we just skip that software to the HLS, we'll actually get a variant that is slower. And here with our optimization, how to include more of those elements so that we have some spatial parallelism within the FPGA, we get a speed of up to 8.6. But this, as I said, these are some preliminary results, just to give you an idea of where we are going with this. Okay, but this is FPGA. This is not very emerging. So let me talk a little bit about some emerging technologies that we have been looking into. So this is a figure that you saw before. This is not from us. This is from IBM. They were showing how they have a prototype of this PCM memory, and maybe some of you know what that is. What PCM means is this a kind of a memristive technology where the cells are memristive devices. You can program a resistivity or a conductance in those devices. So now, if you pass some analog voltages to those resistive elements, you actually get a dot product of the voltages and the conductances. And so that's why it is so interesting to look into PCM computing, because in PCM computing, when you put an address and you put those addresses into the weights, what you actually get in this current here is an analog value that corresponds to the dot product. So in principle, if you have a crossbar like shown here, you can then do matrix multiplication in constant time. Okay, a very interesting technology. You can also do that with rerun, resistive run. Another one is something that we work with Stuart Parkin. So he proposed this kind of racetrack memory. These are magnetic nanowires where you can put bits very densely packed in an array. And there are people working on how do we do in-memory computing in these magnetic nanowires. And here's just an example of one of those. And we're working also with people on how to build systems around this in-memory computing in racetrack memories. So in a collaboration with a bunch of people that you see here in the paper below, you see how we again use MLIR and some of the dialects in MLIR to do some optimizations that are specific for this computation in memory array with PCM. And so we build that so that now you can write code for machine learning using a machine learning framework like tensor comprehension. In this case, a guy wrote a front end so that code for tensor contractions could be lowered into the MLIR infrastructure, and it passes through our multi-level compilation step. And at the end, we generate code for the host, and we configure the crossbar array for doing computations. And now since we have a compiler, now we can recognize when do we have those patterns, or maybe from a DSL, we can now transform the code so that we can profit from the in-memory acceleration. So for some of these applications, so here you have a bunch of applications. For some of these applications, the one that have a lot of matrix multiply, for instance, this MLP3, you see that the software version is 2 orders of magnitude slower than any of these ones that are accelerated with the memristive device. And now we have a bunch of optimizations here. You see different ones, right? And so we can, by optimizing the code for the particular accelerator that we had assumed, you get another bump of performance, which is quite considerable because this is in log scale. There are some applications that do not use so many matrix multiplication. For instance, here, LSTM, long short-term memory. So here, actually, when using the accelerator without knowing much, we're actually reducing performance. Only the last one that is optimized gets a bit better than the baseline software implementation. And this is the picture for execution time. This is the picture for energy. Since these things are non-volatile, they are actually also very energy efficient. And here you see, as I said, for the applications that have a lot of matrix multiplication, again, here you see a 2 orders of magnitude improvement in terms of energy consumption. Okay. So what are we doing with in-memory computing with racetrack memory? So this is a collaboration that we had with people in Pittsburgh, where we took the framework of hyperdimensional computing, which is a very interesting model for machine learning, which is different to the deep neural networks and so on, where kind of the idea, what you have to take from this slide, because this slide is quite complex, is that you embed your data, not 32-bit integers or floating points, you embed those into 10 dimensions, 10,000 dimensions. Like, so a data that could be a 64 floating point bit is now going to be a 10,000 binary vector. And then we work on those 10,000 bit words. And so, of course, working with 10,000 bit words is very difficult in a von Neumann approach, right? Because you have that bottleneck of, you have to take that into the CPU, break that into 32-bit chunks or 64-bit chunks, process them, and go back to memory. So that's very expensive. And now we're working on how to implement that using in-memory computing within the racetrack, and how can we then optimize for the system. Yeah, so I think there's some time to talk about this results. So these are results that we obtained last year. The end last year, you see the runtime again and the energy consumption. So here in both cases, lower is better, and you see in the FPGA and the other one here. So just to summarize the results here, in our simulations, right, we can see that the in-memory computing with racetrack memories is 6 times faster, and 5.3 uses 5.3 less energy than the FPGA accelerator. And in previous work from other people, we can see that the FPGA accelerator is way more efficient than doing this on a CPU or a GPU. So this is very interesting work. This is we're starting to work on this thing. I mean, not with racetrack memories, we've been working for 3 years, but now we're trying to work on how can we then abstract from this in-memory, new kind of in-memory computing that comes with racetrack memories, so that we can also build compilers to map down from high-level frameworks, from high-level DSLs. Good, let me summarize the talk. So what have I talked to? So I said, tame the ever-increasing system complexity with DSLs. As I said at the beginning, I think it's very important that I'm not saying that optimizing compilers are not interesting anymore. I think there's a lot of value in recognizing patterns in legacy codes. That's very sensitive to coding style, but still doesn't mean that we shouldn't be doing that. I worked for a long time in abstracting parallelism in sequential programs. I think that's still a very important activity. We talked a little bit about DSLs. I show you 2 examples because the time is short. How to expose higher semantics and what kind of things we can do. I had to skip some of the things that we do from this. For instance, the particle mesh abstraction. We can actually check for units, that the physical units actually match, so that you know that the right-hand side and the left-hand side of an expression actually makes sense. Anyway, and I do think that these high-level semantics are key for targeting emerging accelerators, right? As we show for the in-PCM computing. If we cannot understand what a piece of C code is doing so that we can really optimize for an Intel core, is really difficult to assume that we're going to be able to optimize for an accelerator like that. Okay, moving forward, things that I'm interested in is the semantic preserving transformation. So I mentioned that before, that we want to be able to do kind of correct by construction compiler, so that you don't want to be writing in a DSL and then have to find bugs in a Fortran implementation if you're not a Fortran programmer, right? So that's something that I want to avoid. As I said before, I'm very interested in how to abstract across different in-memory computers or in-memory computing accelerators, so that we have kind of a generalizing compilation framework that could allows us to target different accelerators and kind of catering for their individual needs. And then we have a project starting soon to work on that aspect. We want to have a better connection to what we call productivity-oriented frameworks. And with that, I mean in the Everest project that I mentioned before, of course, people are working with higher workflow programs, workflow languages, and we want to be able to hook that so that you're not accelerating the entire workflow, but you want to accelerate the kernels that are down below, and you want this to be transparent and also to be easy to use from a like software engineering standpoint. And that's also related to this very integration into workflows. So with that, I'd like to thank you for your attention, and I'd like to acknowledge some of the funding agencies, also the people in my group. You see there a couple of faces, and also here in this presentation, I talked a little bit about work that I have done with collaborators. Some of them are highlighted here in Volfix. Thank you very much.
Okay, thank you so much. That was very interesting, particularly the part for MLIR for computing in memory. And also we have a couple of questions, if you could please answer them. You'll be seeing a Q&A tab.
Oh yeah, yeah. Kiran Mehta says, how do you say C++ classes compare with higher level abstractions in DSLs? Okay, yeah. Yeah, that's a very good question. And as I said, for instance, OpenFPM is using a lot of C++ classes. And so we have people also looking into that. How can you use expressions? The problem is that you are restricted in a sense to what the C++ compiler can do. Okay, and you're still on the positive side. If you're a C++ programmer, you have the flexibility of C++, right? Which is good. If you're not a C++ programmer, you have the complexity of C++. Okay, so that would be kind of my answer here. So yeah, and that's kind of the trade-off, right? So and OpenFPN in particular, I think I'm a C++ programmer, and I think OpenFPN is an excellent library. It's very good to use. But when we talk to the domain experts, they are of course overwhelmed with all those template parameters and whatnot. And if you get an error, even if you do a very good design and you catch those errors and try to pose those errors a little bit more readable to the programmer, that's still a very hard boundary to cross. Okay. Amon saying this, how have you considered languages like Julia, which aim to solve this multiple language problem? Yeah, sure. Julia, we are familiar with Julia, and at some point we thought maybe this language we can then have that just implemented as a Julia kind of a specialization. So yeah, so I think Julia goes in the right direction as well. So I like that project quite a lot. Maybe just to say that with our collaborators, we are interested in having something that is very tailored to what they are doing. And that's why, so the language design in itself, for me, is not like the syntax. Sure, we have a lot of discussions about the syntax because they want to have it like this. They want to have it almost like a web formula, right? So that part, what I'm interested more is in the underlying abstractions. And so if you can map down to those underlying abstractions from a Julia program, that's kind of an engineering question. I don't see more questions, right?
Yeah, that was all we had from the audience.
Okay.
But I had one tiny, not a question, but more of an explanation. Like you said in the way forward, you wanted to talk about, that right now you have to go back to Fortran and like do the debugging and things, but the way forward would be like semantic preserving transformation, if I'm correct.
Correct.
Yeah, so I mean, if you could just give a little more, like if you could shed a little more light into that, please.
Oh yeah, okay. So yeah, so as you said, right, I think, and that's what I meant with. So I mentioned the abstraction tool. So the abstraction tool is that we don't want to lose performance by introducing abstractions, and the other thing is like abstraction leaking. Like we don't want to have abstractions that leak information, right? It's like if you program today in C. You kind of assume that the thing is gonna run. In reality, there are also bugs in C compilers and so on. But for most of the cases, you program in C and you don't have to go and debug assembly, right? I think maybe 0.0001% of the programmers have to do that, right? And that's something that happens today with DSLs, because in part some DSLs have grown organically. And that's actually an experience that we had when we started working in this particle mesh simulation kind of things. So some people had before us, right? People had already started like trying to build this with DSLs, and what they had, it was like a mixture of tools, like some scripts, some Ruby, some Perl, and it was very brittle in the sense that you would program something in this high level abstraction, but then you get some problems from Perl, or then you get some errors generated in the Fortran code. So those are leaky abstractions. So you don't, and so you can imagine how difficult it is for a programmer to do that kind of stuff. And that's what we're trying to solve with semantic preserving transformations, and also in the case of that particle mesh simulation, doing model-to-model transformations, so that we have a model to the C++ world to which we want to map. Right? We don't model the entire C++ world. We just model the C++ world to which we want to map. And so we just have to check in the design that the way we transform into one model elements into models into the elements of the other model, if that is correct, then we shouldn't get any surprises, and that was kind of the point that I was trying to do.
Okay, we have one more question.
In general, what is your opinion about internal versus external DSLs from the perspective of interoperability of DSLs? Yeah, that's an excellent question. So that's a bit of terminology. So for those of you, when you call a DSL internal, when you kind of embed it into a host language, and you call it external when it is kind of a standalone DSL. So what you've seen us do is that we are actually proposing external DSLs because we want to, I mean, we're in research, so we want to explore the DSL in itself, and we want to explore what we can do with those abstractions. But in reality, it is very important to be able to be interoperable between these DSLs. And that's more or less what I said before with this, being able to integrate that into larger workflows. To give you an idea, in this DSL project, we have people that are developing Python code. There are some people that are developing Rust code. There are people developing different things. Some of them are going into the FPGA, some of them. And I also think that here, or not that I think, here we're also using MLIR as kind of an integration vehicle, right? So because you can use MLIR as a glorified XML kind of for kind of match interfaces and so on. On the positive side, you can leverage a lot of things that are in MLIR, for instance, type checking and all this kind of stuff. And then you can stick together different components of the hardware. Some of them generated from the DSL, external or internal, and some of them then the libraries and the stuff that you want to leverage from the platform that you are mapping onto. So yeah, so I think my answer here, I'm gathering that I'm not really answering your question. So I think interoperability is very important. My point is maybe that you can use frameworks to also make external DSLs talk to different languages. And that's what we are doing, even if we're doing external DSLs. With an internal DSL, it's easier because you are within that language and you don't have to do anything else. That's why my answer was more on the sense of, with external DSLs and proper tooling, you can still make different components written in different language interoperate.
Great, thank you. I think it's also the time slot is up and we're going to move to our next speaker, but thanks again for taking the time and answering all the questions.